Okay, in this video we're going to discuss the work energy theorem. So we've already seen that energy is the ability to do work. So we can say that any work is done is equal to the change in our mechanical energy. And so we have here the work energy theorem states that the work done is equal to the change in the total mechanical energy. So this would be equal to the change in elastic potential, or we'll start gravitational potential energy plus the change in elastic potential energy plus the change in kinetic energy. And so just the work done is equal to the sum of all these changes in energy. Now, of course, we can simplify this down quite a bit. If we're given a problem where we don't have any springs, then we don't even need to bother with the elastic potential energy. Also, if we have no height difference, so something doesn't move up or down, then we wouldn't have to bother with the change in gravitational potential energy either. We just have the change in kinetic energy there. Which sometimes, if the work done is equal to the change in kinetic energy, we call it the work kinetic energy theorem. But really, it's just a simplified version of the work energy theorem. So let's take a look at how we can use this to kind of simplify problems we've done before. The work energy theorem is incredibly useful for putting Newton's laws and kinematics together in a very compact form and solving simple problems more easily, or solving more complicated problems in a not too difficult way. So let's take a look here and say we have this runner sliding into a base here. Let's say that he was over here. Once he started sliding, he had some kinetic energy here, Ke initial. And we'll actually say let's give it a value. We'll say it's 100 joules of kinetic energy. And then he comes over here and he has some final kinetic energy as well. So Ke final. And let's say that this final kinetic energy, this is 1/2 mass times the final velocity squared. And if he comes to a stop over here, then the final velocity is 0, and so then his final kinetic energy would be equal to 0. So we can say that the work done is equal to the change in the mechanical energy. And so since I don't have any springs, he didn't slide into a spring, there is no height change. He's at the same elevation when he started sliding as he is when he finished sliding. All we really have is a change in kinetic energy. So this work done, I put an F here. This is a little premature, but this work, the only thing doing any work is friction. So it's actually going to be the work done by friction is equal to the change in kinetic energy, because the only thing acting in the horizontal direction, or the x direction, if I give a notation like this, the only thing doing work in that direction is friction, right? It's the only force we have in that direction. So the work done by friction here is going to be equal to, well, we have the final kinetic energy minus the initial kinetic energy, right? Which is then the final kinetic energy was 0 minus the kinetic energy was 100 joules. And so we have this work done by friction is equal to negative 100 joules. And now friction will always do negative work, right? Because it will always be in the opposite direction of the displacement. So we have friction is off to the right. If we were to calculate this, this frictional force is positive times the displacement is negative, we would have a negative work. So we know that the work done by friction is going to be our frictional force, negative the frictional force times the displacement, right? We have a negative work there, and F here is the magnitude of the frictional force. And so then we can say that the negative of the frictional force times the displacement is equal to negative 100 joules. And they give us here, they give us the frictional force, the magnitude of it is 450 newtons. So we can say that negative 450 d is equal to negative 100. And then we can find out what the displacement is. So a very succinct solution to this. Otherwise we would have had to find the acceleration and then plug that into our kinematic equations. And this actually just simplifies it down quite a bit. So once you get really good with the work energy theorem, problems are much simpler. So we can find D. And of course, I could have given you, maybe an initial velocity and a coefficient of friction, and we could have, put a few more steps into here, but it still wouldn't have been that difficult. It actually would have been just, we'd have negative, if he's on a horizontal surface, we'd just have negative mu k mg d is equal to negative 1/2 m times v initial squared, and it would, of course, masses would cancel out here, and we can solve it from there. So it becomes a very nice, very succinct equation. Let's take a look at another example where we have a height difference here. And so we have this guy pushing up the ramp, and let me give a coordinate system here. We'll call the positive direction to be up the ramp, positive x, and a positive y to be out of the surface of the ramp. So he's pushing in the positive direction, friction is acting in the negative direction. We also have some weight pulling down that way as well. And so we can say that the sum of all the works, that's really, I should have said the net work is equal to the change in mechanical energy, W net. This is going to be equal to the change in energy here. So all the work, if we have this angle is theta, and let's say he's pushing parallel to the incline, then the sum of all the works, or the net work, is going to be the push, the force of the push times our displacement. Let's say it displaces, some distance. Let's say it goes up to here. So it starts right here, this bottom corner, and then it goes up to right here. So this is our displacement D. So the work done by the push is force of the push times that displacement, plus the work done by friction is going to be a negative frictional force times the displacement D there, plus now gravity is going to do work down the incline, right? We have some portion of our gravitational force which is down like this, and when we rearrange our coordinate system to be parallel and perpendicular, I don't need to worry about any force, any work being done in the direction perpendicular to the incline, because it doesn't move in the direction perpendicular, it only moves parallel. So no work is done in this direction here, in our positive y direction. And so we have the work done by gravity would be a negative mg sine theta. And so this is all the work's done, and this must be equal to the change in mechanical energy. And of course, we don't have any springs here, and let's just say that it starts at rest here, and then it ends up at rest here. So we have no change in kinetic energy either. Let's say both at V initial, and of course I would need to tell you this, V initial is equal to V final, which is equal to 0. And so then we can say the sum of this work would be equal to the change in the gravitational potential energy. And so this basically, I won't finish up the whole thing here, but this means that we have the force of the push times the displacement minus the frictional force times displacement minus mg sine theta is going to be equal to mg, and then the height would just be, it's just the vertical height that comes in here. So it went from here to here, and so then this is h. It's not the distance d, but it would be the vertical height. So just mg h. And so then we can use the work energy theorem to calculate how high it goes, or how hard he pushed, or the work done by the man, or the work done by friction, any one of these. So work energy theorem, very powerful way to solve Newton's laws and kinematic equation problems.